Section 8.7, Indeterminate Forms and L'Hopital's Rule. When finding limits of expressions which are in indeterminate form, that would be 0 over 0 or infinity over infinity, so called because they neither guarantee a limit exists, nor do they indicate what the limit is if it does exist. We can try rewriting the expression. So we're going to consider these two examples. Here's the first one. The limit as x goes to 2 of x squared minus 4 over x minus 2. Now we can see, here's the proper way to write this. The limit as x goes to 2 of x squared minus 4 is 0, and the limit as x goes to 2 of x minus 2 is 0. So we can see that we have indeterminate form. The limit of the top goes to 0, the limit of the bottom goes to 0. You can write these little arrows that this goes to 0 and this goes to 0, but that is not what you should be doing. You should really write it out like this. So this tells us we have a problem. Now, prior to this lesson, what we did, if we could do some algebra, was do the algebra. And we can see that we can factor the numerator and we can cancel the common factor and we get this and we can solve it. Also, you might recall this situation. Remember the limit as x goes to 0 of, this should be sine u over u. So if my u is 3x, I need the 3x down here. So I'm going to multiply and divide by 3 to get that. And this is the limit as, now, when I say x goes to 0, that really means as u goes to 0, because if x goes to 0, 3x goes to 0. So the limit as u goes to 0 of sine of u over u is, well, we know all of that is 1 times the 3 that's out there. So we have 3. So we had a theorem we could use here. We had an algebra process we could use here. But there is another method we can use to evaluate the limit of a function that is in indeterminate form. And that process is to find the derivatives of each of those functions and then apply the limit to those derivatives. So if we look at the first example again, we know that this is going to go to 0 and this is going to go to 0. Remember, proper way to write this is like this. So I'm going to take the derivative of x squared minus 4, which is 2x, and take the derivative of x minus 2, which is 1. You will notice if I substitute the limit as x goes to 2, if I substitute 2 in here, I no longer have indeterminate form. And so I can just apply the limit. Now let's look at our second example. Again, we knew that as x goes to 0, the sine of 3x goes to 0, x goes to 0, so we have indeterminate form. Let's take the derivative. The derivative of sine of 3x is, don't forget your chain rule, 3 times the cosine of 3x, and the derivative of x is 1. No longer is this in indeterminate form. So as x goes to 0, cosine of 3 times 0 is cosine of 0, which is 1 times 3, and there is our answer. Now we're going to look at a special case of where f at a equals g of a, which is 0. So we're going to take the limit as x goes to a of f prime of x over g prime of x, so what we just did, taking the derivative, and the limit as x goes to a of f prime of x is f prime at a over g prime at a. And notice that I'm going to use the alternate form of my derivative. F prime at a is the limit as x goes to a of f of x minus f of a over x minus a. And g prime of a is the limit as x goes to a of g of x minus g of a over x minus a. Now you will notice when I have this, I have my denominators which are common, x minus a's, those can cancel, which gives me this, right? And since I started with f at a and g at a is 0, we get the limit as x goes to a of f of x over g of x. So this shows that if I know I have something in indeterminate form, I can also evaluate its limit by looking at the limit of the derivatives of the numerator and denominator. Notice this is not quotient rule. So in its most basic form, L'Hopital's rule states that the limit of an expression that is in indeterminate form can be found by taking the limits of the derivatives of the numerator and denominator if the limit on the right side of the equation exists. All right, so we can see that as x goes to 1, ln1 is 0, and 1 minus 1 is 0. So I have the limit as x goes to 1 of natural log of x is 0. The limit as x goes to 1 of x minus 1 is 0. So I have indeterminate form of 0 over 0. Now, we don't want to ever write that this is equal to 0 over 0. We do not want to write that. Don't do that. Bad. That'll lose you some points. But we can say it gives us this form of 0 over 0. So what can we do? L'Hopital's rule applies because the numerator goes to 0 and the denominator has a limit of 0. I can take the derivative of both the numerator, which is 1 over x, and the denominator, which is 1. And 1 over x over 1 is 1 over x. And now I can apply my limit. I do not have indeterminate form anymore. That's what you have to watch for. Do you have indeterminate form? No, we don't. Let's look at example 2. The limit as x goes to infinity. The limit as x goes to infinity of e to the x is infinite. The limit as x goes to infinity of x squared is infinite. So this gives us the indeterminate form of infinity over infinity. So we can take our derivative of the numerator, which is e to the x, and our derivative of the denominator, which is 2x. Again, do not write that. Do not write this. Right? We want to show that this goes to infinity and this goes to infinity. And the best way to do that is to write the limit as x goes to infinity of e to the x is infinity. The limit as x goes to infinity of x squared is infinity. And the thing that happens here, though, after we've taken our derivative, we still have something in indeterminate form. So we have to go through the process again. And now we can take the derivative again. And notice, after applying L'Hopital's rule the second time, we no longer have indeterminate form. And so we can actually find the limit, which is infinity. Example 3. So the limit as x goes to infinity of natural log of x is infinity. And the limit as x goes to infinity of the cube root of x, which is x to the 1/3, is infinity. So we have the indeterminate form of infinity over infinity. So we can apply L'Hopital's rule. L'Hopital's rule gives us this is 1 over x. This from x to the 1/3 gives us 1/3 x to the negative 2/3. Now, as x goes to infinity, this now goes to 0 and this goes to 0. Because this right here really is 1 over 3 times x to the 2/3. That x to the negative 2/3 actually gives you 1 over the x to the 2/3 with the factor of 3 in front. So this goes to 0 again. So now we have the indeterminate form of 0 over 0. Rather than taking the derivative again, let's see if we can apply some algebra. Dividing by 1/3 means 3 goes in the numerator, and dividing by x to the negative 2/3 means x to the 2/3 goes in the numerator. So using some aloha, we get that, a lot of horrible algebra. Aloha. And we can see that the x to the 2/3 on top and x on the bottom means I have x to the 1/3 now on the bottom. And as x goes to infinity, I have 3 on top, I have infinity on bottom, and 3 over this would go to 0 as x goes to infinity. Now, could we have applied L'Hopital's rule again? Sure. From here, we could have applied L'Hopital's rule. We would get this, which we could then evaluate. Section 8.7 TPs, number 11, 15, and 19.